Dear ISDA community, thanks for having me in your online format. Today I'm reporting on some work that I've been doing during my PhD with Professor Martin Weissmann on the topic of the ambiguity and nonlinearity in the assimilation of visible and infrared radiances. The goal of today's talk is first to introduce the challenges in the assimilation and nonlinearity of the observation operators, and secondly to present on some recent results towards understanding and tackling these challenges. And what makes visible and infrared observations so interesting? Well, geostationary satellites provide large spatial coverage and a high resolution data in time and space, and the data is also quickly available after measurement. Visible and infrared channels in combination can probe the convective environment even before convection appears through the fact that they can see moisture gradients, we can see cloud top temperature and thereby height, and we can detect convective clouds even before radar. In this talk I'm focusing on two challenges, and one of them is the ambiguity of a single channel satellite radiance with respect to the vertical structure of clouds. This is illustrated on the right, where we have two observations, one from the anvil and one from the convective core of a cumulonimbus cloud. And as the cloud top temperature is the same in both situations, the radiance itself doesn't provide enough information to constrain the vertical structure. Thus, this can lead to erroneous increments. Also, clouds violate the assumptions of data assimilation, since the radiance observation operators become nonlinear, and because of the non-Gaussianity of error distributions. The nonlinearity of visible reflectance is illustrated on the right, in a paper by Stefan Geis, where the nonlinearity takes the form of a sigmoidal function. The simulated visible reflectance is shown against the liquid water path in red and ice water path in blue. Of course, there are other issues, like the model representation of clouds and operator errors, but they are not the focus of this talk. In the end, all of these challenges reduce the effectiveness of assimilating radiances. An interesting fact is that the nonlinearity in the observation operator also introduces deviations in the posterior and observation space. What do I mean by that? Well, usually we think of the posterior in the sense of the optimal interpolation between the prior and the posterior given their variances. This is captured by the first formula and is what we expect the posterior to be. The prior ensemble mean is given by the observation operator applied to each ensemble member state and then averaged in observation space. And the observation is YO. The actual posterior, on the other hand, is a nonlinear function in the sense that the nonlinear observation operator is applied to the updated state of each ensemble member and then averaged in observation space. The updated state is given by the background state plus state increments. The state increments are given by the observation space increments, which are then regressed onto the model space. The observation space increments depend on the updated ensemble in observation space, which is centered around the linear posterior, with their prior ensemble perturbations, which are then contracted by a variance reduction adjustment factor. And since the regression implicitly linearizes the observation operator, the actual posterior deviates from our expected posterior. To investigate ambiguity and nonlinearity, we employed an OSSI, an observing system simulation experiment, in which we simulated a nature that serves as a truth, and from this we generate observations, which we use to do data assimilation. This allows us to precisely quantify error reductions while avoiding the confusing influence of certain errors of operational numerical weather prediction, namely observation operator error or systematic model error, and allows us to focus on the remaining issues of nonlinear observations. The software has also proved very useful for teaching and other colleagues' research. So if you are interested in using the software, I want to invite you to visit my GitHub page or contact me directly by mail. The simulations which we conducted employed the WRF model, the Weather Research and Forecast model, and a domain size of 400 by 400 kilometers, discretized in 2-kilometer grid boxes of a variable depth. The resolved scale from this is about 10 kilometers for horizontal motion, and therefore should be enough to capture the deep convection. Also, we had flat and homogeneous terrain and periodic boundary conditions. The initial conditions, as you can see by the skew-T plot on the right, support organized deep convection. The resulting weather can be seen in this animation of simulated satellite images of the brightness temperature 7.3 micron, where you can see organized deep convection scattered throughout the domain. We generated an ensemble by ensemble perturbations, most importantly by vertical profile perturbations which delay or accelerate the development of deep convection. Also, we added some small-scale horizontal noise which avoids homogeneous initial conditions. The result is that several supercells are triggered at random in different places in the domain, and 4 ensemble members are pictured on the right. Motivated by the ambiguity of single channels, we assimilated both visible and infrared channels in the hope to combine their advantages. And what we could see is that the fraction skill score for strong convection and for precipitation actually improved substantially in the first 2 hours, which can be seen by the time series plot on the right, where the different colors mark different experiments with different observation types assimilated, and the red line shows that the combination of both channels outperforms single channel assimilations and improves the forecast of precipitation and cloudiness. But why? To find out why, we conducted an analysis of different cloud categories regarding the error of cloud water and cloud ice. For the category of ice clouds, we can see that the infrared assimilation actually deteriorated the analysis of cloud water. The visible reflectance didn't improve or deteriorate the cloud water. However, the combination of both channels led to an improvement in the cloud water in the analysis. In the result, in the case of ice clouds, the result was strongly beneficial. In other cases, in other cloud categories, like the water and ice cloud category, we found mixed but also positive results. So the combined assimilation seems to mitigate the ambiguity in certain ice cloud categories, and it seems to be the first study to show this behavior directly. The second challenge of this talk was the challenge of nonlinearity, and this was actually motivated by the study of Leonhard Scheck et al., where they have found that model equivalents have not been drawn as close to the observations as estimated by the LETKF, and that the nonlinearity of the observation operator actually led to analysis errors that were larger than the first guess errors. We tried to and did reproduce this finding in our experiments. And on the right, you can see that the error reduction for separate single observation experiments, and there are certainly cases in which the posterior error is increased over the prior error. However, most observations reduce the error. To demonstrate what happens to the whole ensemble, I'm showing now 2 examples. One is the example of a clear sky observation, where most of the prior ensemble members show a clear sky with a low visible reflectance, but some ensemble members also show a higher visible reflectance. The observation also shows the clear sky value, And if we then apply the formulas for the linear posterior, we see that the ensemble members should be very close to this observation. However, the actual nonlinear posterior shows larger deviations, but changes towards the direction of the observed value. In the second example, we have a cloudy observation with a still mostly clear sky prior. In this case, the linear posterior is also very close to the observed value. Nicely seen is that the prior ensemble is shifted in its mean and adjusted in its variance, but higher moments are conserved. However, in the nonlinear posterior, we actually see large deviations from this behavior. However, most ensemble members show cloudy sky. Then we conducted an evaluation for the assimilation of visible and infrared radiances to see whether the increments, the ensemble mean increments, differ from the expected linear increments. And what we can see is that the actual increments differ from the theoretical expectations, and that there is a systematic and a random deviation. On the right, you can see 1 dot per observation, and the increment at this observed observation site compared to the linear increment. In this case, for the visible reflectance, what we can see in the result is that the ensemble mean increment on both sides far from zero is systematically lower than expected, which means that the effectiveness of assimilating nonlinear observations is lower than for linear observations, than it would be the case for linear observations. And in the area of around zero, at small linear increments, we have larger relative nonlinearity associated to this small first guess departures. And similar thing can be seen in the infrared brightness temperature assimilation, where we have lower effectiveness on the far sides and a high relative nonlinearity for small linear increments. To test this behavior, we tested the assimilation of 2 meter temperature observations, and we can see that the nonlinear increment is very close to the linear increment. There are only minimal differences, which are probably related to the fact that the observed variable is the sensible temperature, and it's a slightly nonlinear function of the potential temperature, which is the state variable, and maybe due to localization. Furthermore, we looked at the ensemble variance adjustment, and it's also affected by systematic and random deviations. On the right, you can see the deviation of the nonlinear variance adjustment from the linear variance adjustment for the visible reflectance assimilation. And the first result to be seen is that the variance adjustment can be positive, so there can be a larger variance in the posterior than in the prior. This has been also seen by example 2, in the case where we assimilated a cloudy observation from a mostly mostly clear sky prior. And secondly, the variance adjustment is always less strong than the linear variance reduction, and the variance adjustment seems to be lower than the mean square error reduction. This means that the assimilation tends to make the ensemble underconfident, which could counteract the overconfidence that's usually seen in numerical weather prediction systems. And the second example can be seen now on the right with infrared brightness temperature, where we can see very similar results with sometimes larger variance in the posterior, less strong variance adjustment than in the linear case, And this leads me to the summary of my presentation, in which I want to conclude firstly that visible and infrared observations can be of high potential impact despite the violated assumptions of linearity and Gaussianity. I didn't touch upon this very much in this talk, however, that's what we already have seen in a previous paper. Secondly, that the combination of visible and infrared observations is really crucial to reduce the ambiguity of information. That's a paper which is currently under review but also available as a preprint. And lastly, the estimation of nonlinearity deviations improves our understanding of nonlinearity effects and may pave the road for a potential compensation of these undesired deviations in the future, which could improve the effectiveness of assimilating nonlinear observations. And we expect to submit a manuscript in this regard very soon. With this, I want to thank you for your attention, and I would be happy to take questions by mail or in the Yopad. Bye.